Okay, so new material. Pretty exciting, actually. We're going to get to basically learn how to prove the Gauss-Bonnet formula. We were talking about soap bubbles earlier, and there's one thing I didn't mention to you, and that is something called the isoparametric inequality. And this is a fun topic, okay? But it actually plays an important role in differential geometry. Which is, imagine you have a fence of length L, and the question is, what's the maximum amount of area you can enclose by that fence, right? So this would be the, I think, two-dimensional isoparametric problem. So what shape has the most area for a given circumference? Anybody want to make a guess what the optimal shape is? Circle. Yeah, a circle. Right? It makes sense, right? And if you get a circle, what you'll notice is that L squared, well, what is L for a circle equal? L is equal to 2 pi r, right? And then A is equal to pi r squared, right, for a circle, a radius r. And then you notice that L squared, therefore, is equal to 4 pi A in this case. You guys agree? You all see that? Notice how everything scales correctly. Length squared is area, right? Okay, so that's just dimensional analysis. And then, so the isoparametric inequality is, in fact, that's the greatest possible area. So any other area with that length is going to be less. So that's the isoparametric inequality. It has the content that says that a circle or a sphere is optimal. Now I've given away the answer to one higher dimension, right? Which is, now imagine you have a soap bubble, right? And it has a volume in there, and it has some surface area A. Anybody want to guess what the optimal configuration is for a soap bubble to minimize area given a volume constraint? It's trapped air, and the physics says minimize surface area. We all know what the answer is. It's a sphere, right? And you can work out, okay, what is the volume for a sphere? The volume is for a sphere is 4/3 pi r cubed, right? And are you all done there?
No, the assignment on Grayscope closed.
Oh, whoops.
But I have the PDF on my phone now.
Okay, I'll fix it. You have the PDF on your phone now. Okay, so I'll fix it this afternoon and just upload it for you. Awesome. Just make it easier for me. Great. Okay, that goes here. Anyone here? I think you might have left. Did you take the? You already took the test, right?
Yeah.
Okay. And did you upload it? Okay. To Gradescope. Okay. Okay. So where is it? Is here? It's going to be. Oh gosh. V. There's going to be some constant, right? Times a to the 3/2. Okay? And you can figure out what that constant is based on the sphere. Do you guys agree? And that's the isoparametric inequality. Just like we figured out this constant here from looking at the sphere, the one-dimensional sphere, a circle. Okay. So now how do you prove this? That's a pretty interesting question, isn't it? And there's a proof using the divergence theorem. And I don't think it's in the book. I don't think it's in the book. Yeah, it's kind of a fun topic I like to share. I'm not going to test it, but here I'll show you what the divergence theorem can be used to prove. The way it works is you say, what we're going to do is we're going to go ahead and prove this inequality here. And the same proof will also work in higher dimensions, okay? And but I'm not going to prove it in higher dimensions. Let's prove that L squared is greater than equal to 4 pi A. This proof is quite remarkable. It says basically imagine you have some shape here. And what we want to do is, and this is in some, I think I'm using like the XY plane. And now let's map this to another two-dimensional space. And I need two other coordinates. Let's just use u and v. It's not a u and v as in our coordinate chart, just two other coordinates, okay? And what I want to do is I want to take something here of area A, and I want to map it to a disk of area A. Okay, same area A here, okay? But I want to define the mapping in a precise way. Okay? And so what's the precise way? Well, what I want to do is I want to take vertical strips. I want them to get mapped to vertical strips. And furthermore, I want, if there's a little area A on this side to the left of the vertical strip, I want the amount of area on this side also to be little a. Okay, so now we understand which vertical strips gets mapped to which vertical strip. And then what I want to do is, if you're a third of the way down here, then I want you to go to a third of the way down here. So just map it proportionally, that line to that line. Just stretch it by a constant factor everywhere. That defines a mapping phi of x comma y, into the UV plane. Okay? And in fact, you could say that this phi of x comma y is equal to, and there's a u, it's really a u of x, all right? In other words, what the u value is only depends on the x value here, right? Whatever your x, if you have the same x value here, you always get the same u value over here. Okay, so the u is u comma v, but u just depends on x, and then v, that depends on x and y. Right, because if I figure out what the v value is, first I have to figure out which line goes to which line, so that depends on x. And then I go a third of the way down here and go a third of the way down there, and that depends on what the y value is here. Okay, so I get a mapping of that form. Are you taking the exam?
Yes, sir.
You have taken it?
No.
Okay, you're here to take it. Okay, great. So, just excuse me for a second. Just follow me. Yeah, you can take your book back with you.
Oh, okay.
We need to scan it. He wants us to scan it. He'll give it to you, and you scan it.
That's all. Sorry. You didn't see that on the. You said it.
He said it verbally. I was not in the same mind to understand verbal instructions.
Now it's the.
Okay. So, to repeat, we're proving the isobarometric inequality L squared greater than or equal to 4 pi a, where that inequality captures that a disk is the optimal, right? That's the optimal. You get the maximum volume inside that given perimeter. And the way we're doing it is, given some random shape, we're going to map to a disk. And this is a very clever proof. I'm about to show you magic, okay? You guys have like magic tricks? Okay. This is like a math magic trick. Okay, like how someone came up with this? Well, I sort of kind of know. I'll tell you afterwards. Let me show you the idea, then I'll tell you how people come up with stuff like this. Okay? Okay, so we're doing a mapping from the interior of this region to the interior of that disk. These things have equal area. Vertical lines get mapped to vertical lines, such that the area to the left here equals the area to the left there. Okay, that's well defined, right? And then we map this line to that line. They may not be the same length, right? And so we have to stretch it proportionally, where the top point here goes to the top point there, the bottom point here goes to the bottom point there, and then proportionally along the lines get mapped in. And that means we get a mapping phi of that form. And furthermore, if we look at the Jacobian d phi, right? You remember this from your multivariable calculus class, right? There's your phi. Let's look at d phi. Okay. Now, what is d phi? Okay. By definition, it's the partial derivatives of u and v, right? So it's u x vx, and then it's u y vy. You may recall that, right? That's your definition of Jacobian matrix. It's all of the possible derivatives. First partial derivatives. But here's the thing. Remember, u is just a function of x? There is no y there, right? So uy is 0. You guys agree? First with respect to y is 0. So we can just erase that and put a 0 there. So our Jacobian is of that form. And the other thing that we'll notice is y'all remember that let's talk about this map. And I claim this as an area preserving map. Now, what do I mean area preserving? What do I mean is the determinant of this map is going to equal 1, right? Remember, if you take the Jacobian and you take the determinant of it, right? That tells you how much areas get stretched, right? And the determinant, of course, is this times this minus that times that. So this is ux times vy minus 0. And the claim is this equals 1. Now, why is that? Why is this an area preserving map? The reason it's an area preserving map is because what I'm trying to say is if you take a tiny little rectangle over here, it'll map to a tiny little rectangle over there of the same area. And in fact, any region over here will map to a region over there of the same area. Let's prove it for tiny little rectangles. Everything else is made up of tiny little rectangles to a good approximation. Okay, how do we prove this? Well, if you have area A over here and area A over there, now let's take this line has, suppose that you go up an extra delta A, right? Well, that means it gets mapped to the line over here where you also go over delta A, right? So the point is that everything inside this strip, this strip of area delta A gets mapped to that strip of area delta A, right? By construction, right? Because the areas to the left are the same, right? And so this is A, that's A plus delta A, right? The difference is delta A. And so the area over here is A, that's A plus delta A, so the difference is delta A, right? And so that strip of area delta A gets mapped to that strip of area delta A. And then it's proportional, so if I go with 30% down here and 35% down here, and I go 30% down here and 35% down here, I get 5% of delta A here and 5% of delta A there, right? And so that rectangle gets mapped to that rectangle, they have the same area. And so this argument is actually rigorous. You take limits and stuff. All right, so it so happens that this is an area preserving map, meaning that, in fact, take any region here, inside here, what it maps to over here will have the same area. Because these are made up of tiny little rectangles, and look at the image over there. Those are rectangles as well, and so forth. Or parallel, quadrilaterals or whatever. Okay, parallelograms to some approximation. Okay, so now what we've constructed a map, and we have an algebraic property about it that's pretty cool. And so what is the area over here? Well, the area, you take, let's say this region over here, in my notes I have, the region is R, okay? So we call this region here R for region, okay? You take the double integral, I'll use double integrals, so I'm sure why not, okay? The double integral, okay, an integral over R of 1 times dx dy, that's how you find the area of this region, any region in fact, right? But then this is equal to the integral over R. Another name for 1 is the square root of ux vy, isn't it? Because ux vy equals 1. Okay, now you might be, why would you do that? Well, it's true. Okay, just bear with me for right now. Now, there's something called the AM-GM inequality, arithmetic mean, geometric mean inequality. And that is that the square root of AB is always, wait a second, which is bigger, look. Less than or equal to A plus B over 2. Okay? This is the arithmetic mean. Take two numbers A and B, you average them, right? And that's your arithmetic mean. This is, let's say for A and B positive, okay? That's the geometric mean. So what is the geometric mean? It's you multiply the two numbers and take the square root. So for example, the geometric mean of 2 and 8, right? 2 times 8 is 16. Take the square root, I get 4, right? And so the point is 4 is in the middle of 2 and 8 in the sense that you have to multiply by 2 to go from 2 to 4, and then you divide by 2 to get from 8 to 4. You guys get it? So it's sort of in the middle from a multiplicative standpoint. So they call that the geometric mean. Who knows why they call it the geometric mean? Now, why is this true? This is a basic inequality. You may have seen it before. But here, just square both sides, and you get a. This is the same thing as showing that. Well, let me multiply by 2 and then square both sides, and then you get this, right? And you might be like, well, why is that true? Well, y'all remember what a plus b squared is? This is equivalent to the statement a squared plus 2ab plus b squared greater than or equal to 4ab. But then that's equivalent to the statement that a squared minus 2ab plus b squared. But remember this, what this is, this on the right here is just a minus b squared. So the way you actually prove it is start here and go the other way. So I came up with the proof by working backwards, sort of. Like this statement's equivalent to that, equivalent to that, equivalent to that. And so another way you can think of it is this is clear. Anything squared is positive, right? But when you multiply it out, it's this. Add 4ab to both sides, you get that. But when you the minus 2ab becomes just plus 2ab, which is this, right? And now just take the square root of both sides and divide by 2, and you get your AMGM inequality. Fair enough? By the way, if you think this is cool, there's the most general inequality of this form is called Jensen's inequality. And if you want to learn all about super cool inequalities, look up Jensen's. Is it Jensen's or Jensen's? I'm not positive, actually. So look it up, learn it, and then come tell me how to pronounce it correctly. I kind of think it's Jensen's inequality, but not positive. And this, by the way, is not just one inequality. It's a whole. It's a whole class of inequalities. There's an infinite number of inequalities like this. For any convex function, you get an inequality. This one comes from log x. Y equal log x is convex, and that's ultimately the reason you get this inequality. Okay, I'll give you throw it out there. Okay, so anyway, here's the point. We can apply this here. Now, by the way, ux and vy are both positive. Why? Because as x is increasing, u is increasing, and as y is increasing, v is increasing. So these are both non-negative numbers here. In fact, I think they're both typically positive, but certainly non-negative. And so we can apply the inequality. So therefore, we can say this is less than or equal to the integral over r of ux plus vy over 2 dx dy. Okay. And okay, so just to summarize, we have this amazing, weird idea to define this particular mapping. Why are we doing that? Okay, who knows, right? We look at the Jacobian. We see that the determinant of the Jacobian is 1. And then we make this weird substitution here, right, where 1 equals that. Okay, I guess it's true, right? Then you use AMG inequality. Okay, fine. Where is this all going, right? There's another trick we're going to have to do, which is this phi is on the one hand some map, right? If I just give you algebraically this thing right here, you say, oh, that's a mapping from a two-dimensional space to a two-dimensional space, right? But it's also a vector field, right? If I just said at each point of x and y, I have a u, comma v, I could think of it as a vector field over here, couldn't I? I could, right? And if I have a vector field, I could apply the divergence theorem. Now, I could draw the vector field over here, right? But it might kind of clutter things up, so I'm tempted not to, okay? But just now what I want to do is forget this picture for a second and just think of this as a vector field over here. At every point x and y, I've got a vector. Right? And if I do that, then ux plus vy, that's the divergence of that vector field. And so what I have then is I have equals. By the way, this doesn't equal a. This equals that, okay? So, go to the next line, okay? This equals the, 1/2 the integral over r of the divergence of phi, thought of as a vector field, dx dy. True? Divergence theorem. And okay, that's just the definition of the divergence. We take the 1/2 out. Ux plus vy is, x derivative of that plus y derivative of that is the divergence of the vector field. Okay. And now let's apply the divergence theorem. Why? If you got to use big theorems to get big results, right? We got to apply theorems, right? So this is integral over a two-dimensional region of a divergence. Okay, what does the divergence theorem tell us? Well, that's going to equal 1/2 the integral through the boundary of r right? The boundary of R is just this curvy path here, the one-dimensional path, of the flux of phi, right? So it would be phi dot product, NDS, or whatever y'all are most, we have to look at normal vectors here. I'll use n hat, right? And so we'll call this n hat time, and then d little s, that's the thing you integrate to get length. Okay? That's the divergence theorem. Divergence theorem right here. Divergence theorem, okay? And then you're like, okay, fine. We have an inequality. Let's say, can we bound that? And the answer is yes, because we got 1/2 the integral over the boundary of R. When you have the dot product of two things, remember when you have a dot product that v dot w is less than equals length v length w times the cosine of the angle between them, right? So therefore, that's always less than or equal to the length of v times the length of w, with the equality if and only if they're parallel, pointing in the same direction. Okay. And so this is less than or equal to, well, I know the length of n hat. N hat is a unit vector, right? So that's just going to be 1. But what's the length of phi here, right? Well, if we give this radius r, right, then it's going to be less than or equal to r, right? Because, here it's just a vector field, but this vector field is also a point over here, and that point here is within, this is a circle, right, or it's a disk, right? And so this is always has length less than or equal to r, and that has length exactly equal to 1. So this is less than or equal to r times ds. Okay. Now, what is that r? Well, this is a disk, so the point is the area is equal to pi r squared, right? And so r is equal to the square root of a over pi, right? Okay, and so then this is equal to, so what does this equal then? This equals that r, this is a constant, right? So what we get is r, and we integrate over the boundary. By the way, I'm using capital R here and here. Now I'm regretting calling that r. Are y'all, okay, let's call this little r. Okay? Because I already have a capital R, it's that region there, right? Well, now when we integrate over the boundary of R, this boundary of R, let's say it has length L, right? Because we're actually trying to prove the isobarometric inequality over here. The length of the boundary is L, the area is A. And so we're integrating a constant here, so we get 1/2 L times little r, right? But little r is just the square root of a over pi. And then you stare at this, you're like, okay, this is a pretty interesting argument. We have a less than or equal to a bunch of stuff, and then less than or equal to a bunch of stuff, and then you get 1/2 L. This only has L's and A's, and that only has an A in it, right? And so what we've proven then is that A is less than or equal to 1/2 L square root of A over pi. And then square both sides and multiply through by 4, whatever, and we get 4a squared less than or equal to LA divided by pi, divide through, squared, and then divide through by a, 4a less than or equal to L, let's put the pi over there too, right? 4 pi. And then there you go, L squared is greater than or equal to 4 pi a. Magic. That's a pretty cool magic trick, right? So what's the divergence theorem good for? If anyone ever asks you, you just pull this little thing out. I mean, the divergence theorem is a big part of it. I mean, that's sort of the power of it. There's this definition on this map. Anyway, this is actually one of my favorite proofs of anything. I once showed this to a very famous professor at Harvard University, who I won't say any more, I don't want to identify him. And when I showed him this, And he was like, no way. There's no way this is a correct proof. If this is a correct proof, I would have known it already. And he basically said BS. And so he walked in a little bit late on my proof, and so I had to show. It's not my proof. I had to show him the proof again. It's actually been known since the 50s. It's just little known. For some reason, it's not super well known. You can prove, and by the way, this works in all dimensions. There are a few technical details we left out because what if the shape here isn't convex? What if it, folds back on itself? And there's some technical details, but it turns out it all works out. There's something called geometric measure theory, which is the more traditional way to prove these inequalities. You assume that there is an optimal configuration, and the book I think does this kind of proof. The book has a proof of the isometric inequality in there somewhere, but what they don't tell you is that they're assuming something big, which is that there isn't an optimal configuration, namely a SOHO. Okay, they're assuming that. And proving that's actually quite difficult. It requires something called geometric measure theory. But this is elementary. There are no hidden details here particularly. I mean, there are technical details that are easily worked out. There's no huge theory behind this. It really is just a proof using the divergence theorem. Now, how would someone think of this? How could anyone ever come up with this? Does anyone have any thoughts on that? I mean, I'll tell you my thoughts. That's actually a good question. The person who came up with this is, I think Gromov might have had something to do with it. He's still alive. He's an old man now, but he's in France. And I think it was him and someone else, or maybe the other person came with the original idea and Gromov perfected it, or I'm not really sure because I think there's two names attached to it. But first of all, well done. Can we appreciate that whoever did this, well done. You are what we call a role model. That's what I want to be when I grow up, come up with ideas like this, right? Yes. Okay, nice. And you don't need too many ideas like this in your life to where, people will pay you money to do mathematics, right? So this is like, as a mathematician, you can appreciate this. And this is so elementary, that's the thing about it. That's why I said this very famous professor at Harvard was like, no way something that cool exists and I didn't know about it, but it's super. I mean, because it's elementary. This is calculus, right? It's something. Why don't they teach you this in your multivariable calculus class? Right? It's like one of the nicest applications of the divergence theorem around. But I think that the construction of this map is worth thinking about. One thing I'll point out is that if you have a disk, right, and it's already in the optimal configuration, right, then you get the identity map, right? Do y'all see that? So in other words, your map is special. The way we constructed the map, it's basically a translate. All it would be is, it could be off-center disk here, right? But then it just translates it to the center, right? So a disk will map to a disk up to a translation, right? And so I think that's essential. Whenever you have an inequality, and you're trying to prove an inequality, and by the way, I'm famous for proving the Penrose inequality, or Riemannian-Penrose inequality, which is an inequality. And one of the key things is you have to understand the case of equality. The case of equality is a disk, right? So this is a circle with a disk on the inside. You get this construction of the map gives you the identity map. So that's already, so in other words, your argument is going to be special for a disk. And it has to be special for a disk. Why? Because these inequalities have to be exactly equalities in the case of equality. Okay, you can't give up anything because you're going to have this exactly equals that, right? You're going to have L squared equals 4 pi a. So there is no room for error. These estimates have to be exact statements in the case of equality. Okay, so that's a hint at how you might define a mapping. And sure enough, I mean, look. So then, if I challenge you, I said, look, find the simplest mapping that maps any region to a disk, such that you get the identity mapping for a disk, right? Well, I mean, that's one of the easiest mappings I could think of. I mean, it actually is, right? I mean, you come up with a better idea, right? You get what I'm saying? I mean, how many different things could I even think of, right? I mean, less than 10, right? So we have a finite number of simplest mappings you might do, right? And you want it to be geometrically natural, I mean, I don't even know how else to define a mapping. Like, if you think about it, right? It's a weird, clever idea, but on the other hand, give me 10 more mappings from arbitrary regions to a disk, right? It's not that easy to come up with a mapping, isn't it? Is it? So it's like, actually a pretty natural thing to do in retrospect. Okay, so and so what I'm trying to prove to you is it's a finite number of things to try. And then you try them all and then see if one of them works. Okay? And then, okay, you construct your mapping, and then you're like, okay, what's special about this mapping? And then you figure, okay, maybe it should be an area-preserving mapping. That's, again, you want it to be an area-preserving mapping, or maybe it preserves the length of the boundary. But we're trying to prove something about L and A, right? So having an area-preserving mapping, that seems natural, right? Okay, and then so you construct an area-preserving mapping. Well, what does that mean? It means this. That's the algebraic version of it, right? And then you're like, well, how can I express the area? Okay, well, I have this, and I know that's 1, okay? And so then you figure, and then you probably do this, and then you're like, you know what? There is a best theorem in multivariable calculus called the divergence theorem. So I've got a best theorem, and this can be interpreted as a vector field. So why don't I just write down the divergence theorem? Boom, you write this down, and then you realize, oh, the divergence theorem has a ux plus vy in it. Oh, but I have this equals 1. And then you're like, oh, why don't I just do this trick? Right? So you probably come up with this divergence theorem, and then you get this, and then you say, oh, well, what if I do that and connect these ideas, right? And then boom, there you go, it works, right? Yes?
Why and how did we assume that y is 0 again?
Oh, by construction, we said that vertical lines go to vertical lines, right?
So we just arbitrarily decided that's the way it's going to be.
So this is Vx, by the way.
Oh, sorry.
No, excuse me. No, it's u. You're right. It's uy. It's because u is only a function of x.
And that is a part of our setup.
That's the way we constructed it.
It's not like a result of area preserving.
That's
or
correct.
anything. It's
That's
just,
correct.
Okay.
It's because we said vertical lines go to vertical lines, and so your u value over here only depends on your x value over here.
Cool.
Yeah. And so anyway, I hope that gives you an idea. What I've done is I've tried to reconstruct a thought process. And so and if I can convince you that there's a finite number, in some sense, a finite number of things to try, right? Not really finite, more that there is a correct order in which to try things. Like if I said, let's define a mapping, right? I mean, I challenge you to come up with more than 10 different reasonable mappings, right? Okay, so maybe 10 different mappings to explore, right? And then, okay, the divergence theorem. Okay, how do I know the divergence theorem? How come it's not? Okay, what other theorem you want to use? Well, you use Green's theorem. Guess what? Same theorem in dimension 2. Okay, and what other theorem should I use? What big, powerful? There aren't a whole lot of theorems to use. You guys get that, right? So let's say, come on, maybe it's a stretch to come up with more than 3 theorems that might be seem appropriate to try to use as your sort of the power of the theorem, right? And so the point is there's a finite number of things to try. Now that finite number might be 45 things to try. And each one might take an hour. Okay. You said you wanted to be a mathematician. That's what mathematicians do. Okay, so you have 45 hours of work and you get a cool theorem. Now it doesn't even sound that hard, does it? That is what research is. That's how you come up with new ideas. Is you just, do the calculation. How many hours of work would it be? Okay, and then don't panic, don't freak out, don't try to do 45 hours of work in a 3-hour period. It's not going to work, right? Just start being systematic about it and try all the possibilities. And the next thing you know, you find out that you come up with new ideas. And in some way, it's becoming a little bit routine, believe it or not. And the only thing I can say is, let me ask you this question. When I came up with my proof of the Riemannian Penrose inequality, because I can talk about that one because I was there, right? Did I invent it or did I discover it? I discovered it. Right? You discover truth, right? That's all. All you're doing is figuring out what's already true. Okay? And whoever came up with this, Gromov and his collaborator, however the order was, they discovered this, right? And what I can tell you is that the history of science and the history of mathematics says that there's a lot to be discovered. All right? It's like, it's not a barren wasteland where when you explore ideas, it never works out. It's kind of the opposite. It's a gold rush, right? So if you see a bunch of other people come hiking out of a mountain valley and their bags are full of gold ore, right? The point is, just go in there and start digging, right? And so, you know, you might say, but that's hopeless. How could I possibly find gold? It's just ridiculous. I'm going to just dig into the ground. And well, I mean, if everyone else is finding stuff. On the other hand, probably you don't want to go into some place where people haven't found gold, right? So that's why when you go to graduate school, you need an advisor, and your advisor can take you to the mountain valleys that have been successful, right? And here's where there might be some reason to think there's going to be something interesting that comes out. On the other hand, if you're the first person into a new valley, I mean, that could be pretty awesome, right? What if you start a gold rush yourself, right? So, but that's more of a risk, obviously. Okay, so hope you guys enjoyed that. It won't be on the test, yes?
How many finite like pathways were there for the Penrose inequality?
It took, let's see here, I ended my second year of graduate school, which would be 1994. So probably around May 1994, my advisor gave it to me, the problem. And I had my sort of eureka moment. I realized I've solved this in December 1997. So that's 3.5 years of exploring ideas. In retrospect, it shouldn't have taken that long. All right? But, you know, a lot of that was me learning how to be a mathematician. The first summer, and I'll tell you this because it can save you all some time if you go to graduate school. My first summer, I spent just trying the ideas my advisor told me to try. And so that's something that you're going to want to be careful about, is that, you know, your advisor gives you a research project of some kind of problem. And of course, they're going to try to help. And so they're going to say, here, try this idea, that idea, and that idea. So I spent a summer trying these 3 ideas. And I had a great advisor. But guess what? He had already tried all 3 of these ideas. And you couldn't get them to work. So it's like, you know, okay, I mean, at least now we're doubly sure they don't work, right? But this is, you will have your advisor doesn't know how to solve it either. This is the problem, okay? So when they give you, here, try this idea, that idea, and that idea, I'm not saying ignore that. But what I'm saying is don't just do that, because there's a tendency for them to show you the ideas that they couldn't get to work. I mean, look, if they had an idea that would work, they would have already solved the problem. This is the kind of the difficult situation, right? However, what was good is I explored those ideas. I figured out why I couldn't get them to, I couldn't get any of them to work. And then I will share this with you. It was a transformative educational experience I had the summer after my second year, before my third year of grad school. And it was Saturday morning around 9 a.m. and my phone rang, and it was my advisor. And he said, hey, I think I've solved your thesis problem. I think I've solved the Riemannian and Penrose inequality conjecture. And I was like, oh, it sounds exciting. Okay, and so we talked on the phone for half an hour, and he said, here, why don't you come into the office and let's talk about it. This is a Saturday morning, by the way, okay? This guy works hard, okay? The most successful people in the world, they just love what they do. He's not doing it because he has to. He's doing it because he loves it, right? By the way, he works 7 days a week. He does half days on the weekend. So Saturday and Sunday are half days. I bicycle into the office. We discuss it for a few hours. I immediately have reservations. And I point them out to him. I'm like, and it's because his thing was not sharp for the case of equality. And I pointed that out to him, like, it's not sharp for the case of equality. And he recognized, yeah, it is a kind of a problem. I don't know about this. Maybe it's not going to work, right? I mean, I thought about it for another 2 or 3 weeks, and I verified it wasn't sharp for the case of equality, and it didn't work. But it was a brilliant idea. And it changed how I approached research from then on, because then I realized, oh, that's what I'm supposed to be doing. He came up with this completely new idea, sort of like this, right? Imagine an idea like this, super clever, oh my God, but let's suppose at the very end, you work it out, and it's off by a factor of 2, and it doesn't work, right? It's just like, oh, it's so close, right? And you get inequality, but it just doesn't work, right? That happens sometimes. And in fact, it's going to happen a lot, right? You're going to have more ideas that don't quite work than ideas that do work, right? And so, but what I really appreciate about my advisor is he let me see behind the curtain. He let me see him come up with an exciting idea, and then it didn't work out. And I was lucky I got to see it, because guess what? Did he ever write a paper on an idea that didn't work out? No, that's the problem. And there's at least 10 times as many ideas that don't work out as ideas that do work out. And no one ever writes a paper. No one ever wants to talk about their ideas that don't work out. And so it gives everyone else the impression that all these geniuses just all have nothing but good ideas. It's very frustrating if you're having a bunch of bad ideas that don't work out, and all you see about someone else is they have ideas that do work out, isn't it? So when you realize that everyone is having ideas that don't work out, some are really bad ideas, and some are just ordinary bad ideas, and some are slightly good ideas, but they still doesn't do what you want. And there's a whole range, right? And really, it's a quantity thing. And that's what I realized is, okay, time to just start coming up with ideas. And so I came up with ideas. I ended up writing a nice thesis that had made partial progress on the, by the way, I'll tell you what the idea was, is you have a black hole, and I was trying to prove something about the mass of black holes. And my idea, this was my idea, is I decided to blow bubbles around the black hole. And I said, hey, what if we put soap bubbles around the black hole, right? Because these black holes have a geometry, and what if we minimize area with a volume constraint around the black holes and look at the whole family of nested, somewhat you can think of as nested soap bubbles of all different volumes, right? And what if I look at the area as a function of volume? What does it tell me about the geometry of the black hole and the mass and blah, blah, blah? And it turns out it gives you something. And I proved some special cases of the Riemannian-Penrose inequality, which is an inequality about black holes, basically saying that the mass of a black hole is at least the square root of its surface area divided by 16 pi. So I actually was able to get a partial result, like in certain special situations, that soap bubble technique actually gave you something. And that was my thesis. And guess what? People thought it was pretty cool. And so that got me a postdoc at MIT, and an NSF-funded postdoc at Harvard. And that was beginning my career. And then I wrote up that idea. And I think I may have told you this before, but then near the end of my PhD, someone else came up with an even better idea that proved a stronger version of the Riemannian-Penrose inequality just for one black hole. And so that was, I went from having the best result in the world to the second best result in the world, which is good, actually, because you want that. You want a community, right? And what was good about that is that then I was stuck on my idea. So let me tell you something else that will happen to you in graduate school. You'll come up with an idea, and you will fall in love with your idea because it's your idea. Your idea is like your baby, and it's like this is the best idea ever. It's my idea, right? You're biased towards your own ideas. Can you all see that? Of course you are, right? And here's the problem: to your own detriment. It's just an idea. Get over yourself. Just because it's your first halfway decent idea doesn't mean it's the best idea ever, right? Like you should explore other ideas too. Does that make sense? And so I think I was guilty of locking in on my first halfway decent idea, right? In graduate school. Next thing you know, I'm in second place because someone else came up with an even better idea. And then so I went back to the drawing board when I started my postdoc at Harvard, and I talked to the people who came up with Huskin and Illman, and two great mathematicians, and inverse mean curvature flow, another geometric flow, cool stuff. And I studied their techniques very carefully and realized why their idea was better than my idea that I had in graduate school. And I was like, yep, it's better, and here's why it's better. And it's like, and you just have to, you got to be honest, right? And then what I realized what was better about it is that it was a geometric flow. They had figured out how to take instead of having soap bubbles go around the black hole, they took the horizon of the black hole, like a sphere, spherical surface, and they flowed the surface under a certain precise geometric flow. So it wasn't soap bubbles, it was an actual geometric flow of surfaces, okay? It's called inverse mean curvature flow. And I realized if you prescribe the flow exactly, see, a soap bubble could move around, right? When you increase the volume, who knows where the minimum area is? It could be anywhere, right? But a geometric flow, right, that's precise, and you can control it more, and you can understand it better. And I was like, geometric flows are cool. And so then I started thinking about geometric flows also. And then it turns out I found out an even better geometric flow than they had. Well, at least for proving the Penrose inequality. And so that was my December 1997 idea, whereas their technique only proved the inequality for one black hole, I ended up proving the Riemannian-Penrose inequality for any number of black holes. And instead of doing a flow of surfaces, I flowed the whole space. Right? I flowed the three-dimensional space. Take any slice of space-time, and then I flowed it, defined a flow such that when you flow for an infinite amount of time, it comes to a spherically symmetric static black hole solution. Right? And that's how I sort of recognized the geometry of a vacuum, of a black hole in vacuum, by defining a new geometric flow. Okay, and so in other words, it's really by being influenced by my competitors, right? So when you're in graduate school, I had a graduate student, by the way, who his first year of graduate school, when he first got here, he said, "Hey, Hugh, what should I do?" And I said, "Read papers." And then to my surprise, I didn't tell him how many, right? So to my surprise, like, "So how many papers you end up reading actually?" He's like, "Oh, I read 100 papers that first year." I was like, "Whoa." I didn't mean for you to read 100 papers. I just said read as many papers as you can. I probably said something like that, right? And so I read 100 papers the first year, 2 a week, right? And it was like, in retrospect, like, oh, yeah, okay, guess what? This guy is super successful, right? He's killing it. He's got a postdoc at Columbia lined up. He's at the Institute for Advanced Studies for a 1 year or 2 year postdoc right now, right? He's going to do great. So, yeah, read lots of papers, learn as fast as you can, try to get to the edge of knowledge, and then pick some problems to work on and try a bunch of different ideas. And it's exhaustive, just trying all kinds of different ideas is how you make progress. Okay, so anyway, I know some of y'all are going to graduate school. I think a lot of this would apply to physics as well as math and other disciplines, economics, whatever. So hopefully that's helpful. Okay, so let's talk about geodesic curvature. Anyone have questions about isochronometric inequalities before we go to geodesic curvature? Okay. Let's suppose that we have the surface of a potato here. And let's suppose there's a curve on that surface. And let me have just curving one way. I'll have it curve like this, okay? And so what you have is, the ant could be trying to walk in a straight line, or let's say it decides to curve to the right. If it curves to the right, you get the picture as drawn, right? It's curving to the right. And so how do we measure how much if an ant is walking on a potato, how do we measure how much he thinks he's curving? Not how much he's curving in three-dimensional space, but how much he thinks he's curving, right? Because if he's walking straight, but keep in mind, the ant walking on the potato is unaware of the third dimension. So he thinks he's working straight, right? Just like a straight line. His world is a straight line. But then on the other hand, he might decide to curve to the left or curve to the right. Now what we already know is, let's call this let's think it's a unit speed curve. Let's call it beta of s. S means parametrized by arc length. So it's not alpha of t, it's beta of s. I tend to like to use beta when it's parametrized by arc length, just to emphasize it's a unit speed curve. But s is always arc length anyway, okay? So I think the book might do alpha of f or something like that. But anyway, it doesn't matter. The s is important, the alpha or beta doesn't matter. And so in particular, at any given point, that point is beta of s, and then this vector right here, right, that's the unit speed direction t, right? And that t is equal to beta prime of s, right? Now we have this trick that we use over and over again, is that the length of beta prime of s is 1 everywhere, right? So the dot product of beta prime of s with itself is 1. Agreed? Which means that if we take dds of both sides, we get 0 equals 2 beta prime of s dot product beta double prime of s. So in other words, calculus tells us that, that the beta prime of s is perpendicular to beta double prime of s. Okay, so that's our kind of standard argument we've used many times. And so then you're tempted to say, okay, this beta double prime of s, this is a three-dimensional vector, and it can be expressed as linear combinations of an orthonormal frame. Okay, so let's do, for example, it's some constant times u plus some constant times another unit vector plus another constant, let's say, times t, right? So I put t at the end here for a reason, right? And the reason is that we actually know this constant here is going to be a 0, right? Because beta double prime is actually perpendicular to t. T is just beta prime, right? Now, what's an orthonormal frame that we can use with u and t? Now, what's u? U is the uninormal perpendicular to the surface, right? So we had this, we're trying to do a Frenet frame kind of thing, right? Now, how did we get the Frenet frame? The Frenet frame was defined in terms of, first we had t was our first vector, right? Then we looked at the derivative of t, essentially. That gave us this n direction, right? And then we took t, was it t cross n? And that gave us b, right? Okay, now here we're not going to do that. Here we want to understand sort of a Frenet frame, but something that's natural with respect to this surface. And so we actually have another unit vector that's natural already, and that's u. And u and t are already perpendicular, right, by definition, because t is in the tangent direction, and u, by definition, is perpendicular to all the tangent directions. Agreed? And so what we can do then is say, okay, we have one unit vector, u. So u is coming, this is length 1 as well. These both have length 1. They're perpendicular. And this t here, they're perpendicular. And so now what's the other one going to be? Well, why don't we just do u cross t? And then we know that how that works, right? We use our right-hand rule. And so if this is going out of the board, u cross t is going to be pointing, let's see here. It's going to be pointing to the left there, right? Well, his left, as he's going this way, right? So anyway, some vector here, u cross t. Fair enough? Did I get it right? Yeah, u cross t. This u is going out of the board. It's hard. My picture might not be perfect, right? I'm not having u come out of the board. It's not going into the board. It's going out of the board the way I meant to try to draw it. So then u cross t is going to be going like that, right? And so what we can do then is say, well, this beta double prime of s is linear combinations of this orthonormal frame. But we know that beta double prime of s is perpendicular to t because t is just beta prime of s, right? So we know the coefficient here is 0. Because remember, how we find these coefficients, you just take the dot product of beta double prime of s with this, right? And so we know what's this coefficient here? Well, this coefficient here is just beta double prime of s dot product u, isn't it? That's how you find the coefficient. Agreed? And the same thing here. The coefficient here is beta double prime of s dot product u cross t. And it's no different than for I, j, and k, right? The way you find the coefficients is you dot product with each of those vectors, and that tells you the coefficient. Now, if you stare at this a bit, there was a theorem we proved before about normal curvature, or I like to call it cross-sectional curvature, is that this right here is actually just the normal curvature in the beta prime direction, beta prime of s direction. That's what this term right there is. Y'all remember that theorem? I think it was, we might have had an alpha prime to t there or something like that, right? But the point is, that was a theorem we proved about normal curvature. Is that remember the reason we even call it normal curvature is that the curvature vector in the normal direction. Remember? That's why they called it normal curvature, right? That's the curvature vector in the normal direction. So normal curvature. I refer you to that section. And so that's what this first term is here times u. And then we have this new thing here. And this thing right here, let's just call that geodesic curvature. Okay? And so this is where we define this new concept, geodesic curvature, to be just beta double prime of s dot product u cross t. And so this is our new concept. Okay, now, in other words, old concept was normal curvature. New concept, geodesic curvature. So another way to think of what we're doing is, you have a curve on a surface. How much is curving in the normal direction? We already discussed that. It's called normal curvature. how much is curving in the plane of the surface of the potato. That's the new thing called geodesic curvature. And what you'll notice is we're taking the beta double prime of S and we're dot producting it with the vector going to the left. U cross T. What is U? You see, if you're going on the surface here, I was saying U is going up, right? We'll call that up from the point of view of the ant, right? Then U cross T is to the left. This is the left vector, or you might call it. Maybe it should be called L. They don't do that, right? But this is the vector going to the left from the point of view of the ant. And so how much you're curving to the left is what that is. So if the ant's walking straight, the geodesic curvature is 0. My geodesic curvature is 0. And then if I curve like this with radius 1 over, with some radius r, then my geodesic curvature is 1 over r. So how much you're curving to the left if the unit vector is pointing up. Yes?
Why don't we care about how much we're curving right?
What's that?
Like curving to the right instead of curving to the left.
It's completely arbitrary. You could have defined it the other way.
Right.
Convention. I actually just want you got me looking at my notes. Is it U cross T or T cross U? Like, okay, it's just a convention, something to understand. It's going to be consistent with the book. You could define it the other way. And by the way, it is to the right if the U happens to be pointing down, right? Because if U is pointing down, then U cross T would be U cross T would be pointing the opposite direction. All right, so if I change the sign on U, it changes the sign on U cross T. Fair enough? Okay, so that's what geodesic curvature is. Now there's a theorem, and this theorem reminds me of the theorem we had for Gauss curvature. Y'all remember that really complicated formula with the EF and G's for Gauss curvature we came up with? Well, it turns out there's a formula with EF and G's. You can come up with geodesic curvature as well. And so basically what you do is you say, okay, suppose this is my UV. By the way, this is actually my coordinate chart again, okay? So now I'm using U and V the way we traditionally do. And this is a coordinate chart on part of a potato. Right, this is an X, Y, Z space. So we have this X of U comma V, our usual setup. And then you can talk about a curve over here. This curve here is U of T comma V of T. I mean, we want it to be a unit speed curve, so let's call it U of S comma V of S. But realize this is, you compose it and you get a curve over here, right? And this curve over here is what we're calling beta of S, right? And the whole point is that beta of S is equal to X of U comma V, but U and V are both functions of S. And then we'll say that this is a unit speed curve, beta of S. Okay. So this is not necessarily unit speed, okay? In the coordinate chart, okay? This is just some coordinate chart. It's like, the thing where Greenland looks really too big and Antarctica is infinitely big and stuff like that. Lengths and areas are distorted here. It's just a coordinate chart. This is where we have a unit speed curve, beta of S. And we can set beta of S up like this. And then if you do that, we get a theorem. And the theorem says that the geodesic curvature can be computed in terms of the EF and G's and the U primes and V primes and U double primes and V double primes. And it's the square root of EG times minus E. You see, I do not have this memorized. I don't know who in their right mind would. Then you have a U prime of S cubed plus you don't need to write this down. I even wonder where I should write this down.
switch parameters.
Huh? Oh, sorry. Yeah. That's what happens when you do something different than your notes. Okay. So u prime of s, I put extra parentheses here. I'm not changing anything. I'm just getting rid of the parentheses. You just, no, that's not necessary. Okay. All right, so there we go. Plus, I guess, might as well keep on going here. Plus g sub v over, this is how you know it's a long theorem. When it, to state the, like, how long is the proof if this is how long the theorem is? But that e sub v is a partial derivative, e partial derivative with respect to v. And then you get u prime of s, v prime of s squared. Thanks for the correction, by the way. Plus g sub u over 2e v prime of s cubed. And then, okay, plus u prime v double prime of s minus u double prime v prime. There you go. That was actually time for my arm. Workout. Okay, now how do you prove this? Well, it's kind of obvious, really, right? No. It's in the book. Okay. Let me get it started. Let me get it started. Okay. Just. We don't really have time to do the whole detailed proof today. And furthermore, the way to do it is to study the proof in the book anyway. But just to get it started, what you do is you start with this identity right here, right? And then you take the derivative with respect to s and apply the chain rule, right? So for example, what you have is beta prime of s is equal to, this is where you need to know the chain rule, right? X is a function of u and v. So doing the chain rule, it's going to be x sub u times u prime of s, right? In fact, let me put in more details, okay? We're taking the x partial derivative. Now, x is still a function of u of s and v of s, so it's tempting to sometimes drop that off, but I'm going to leave it in, okay? And then times the derivative of the first lot, which is u prime of s. And then plus, do the chain rule, I also take the partial derivative in the second slot, so that's xv of u of s, v of s, times v prime of s. Everybody see that's just a chain rule? Multivariable calculus chain rule. Then remember actually what it's used for, say, every other theorem in differential geometry. And of course, the reason I put this here and that there is because then we want to compute what beta double prime of s is, right? And so now we're going to do the chain rule again, just because it's so much fun. And so what you get, for example, is, okay, now I'm going to take the u partial derivative of this function, followed by the v partial derivative, right? So I'm going to do the chain rule on this. I'm going to get two terms here. I'm going to get two terms there. And that's not counting the product rule. Okay? Okay, so what I have then is x, okay, I get xu, and I think it's u partial derivative, right? And when I do that, now I'm not going to say of u comma v. I'm going to leave that off now because otherwise the equation gets too long. I don't really need to put it there anymore. And then it's times, I'm going to get a u prime coming out plus the u prime that was already there, right? So u prime of s squared plus xuv of u comma v, which I won't write, times, and now I have a v prime of s coming out, but I already had a u prime of s, so I'm going to do a u prime v prime, plus xu times u double prime of s. Okay, that's the product rule. Okay, so I did the derivative of this as the chain rule. And then, so it's derivative of this times that plus this times derivative of that. So that's just doing, I'm halfway done now. Okay, I've done the first thing. And now I have to do, so that was the first line, was this part right here, taking its derivative. And then the second line is taking this guy's derivative. And I say plus, I'll do the second term first. So again, xvv times v prime of s squared plus xuv. So I'll take the u partial derivative, and that's have another u prime coming out times u prime v prime. And then the product rule is going to give me an xv times v double prime of s. And there you go. Product rule and chain rule gives me that. It's all in the book. So that's what alpha double prime, or beta double prime is. And it continues. Now we only have 5 minutes left in class here. Let me point out, I think I can sketch the proof, right? U cross T what is U? U is the vector perpendicular, right? It's perpendicular to what? It's perpendicular to xu. And by the way, we're going to assume f equals 0, okay? So remember the E, F, and G's, we're going to assume f equals 0. It makes things a lot easier. So what is U? U is the vector perpendicular to xu and xv. The problem is xu and xv might not be units. So let's divide by the square root of E here. Remember, E is xu dot xu. Now that's a unit vector. Divide by the square root of G. That's a unit vector. They're perpendicular because f is 0 by assumption. Take the cross product, that gives you U. Okay? So we're assuming our coordinate chart is oriented such that that cross that it gives you U, not minus U. And then you take, so that's what U is. Okay, now that's U cross T. Now what is T? T is that, right? T is beta prime of S. This is T right here, right? Okay, so T is xu times U prime plus xv times v prime. Okay, so here I've left out what things are functions of. And if you simplify this, dot, 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 okay, what am I going to do? Any vector cross product itself is 0. And so, and I'm using the fact that we have an orthonormal frame. And the orthonormal frame I'm using here to do these computations is the orthonormal frame xu divided by the square root of E, xv divided by the square root of G, and U. And so think of this as your I, your J, and your K. I, J, and K, okay? And so up to a rotation, I can think of them that way. And so when you do xu, when you do this cross product that, you get that I cross J is K. So this cross that is that. And that allows you to simplify things quite a bit. And what you get then at the end of the day is that this is equal to the square root of E over G xv times U prime minus the square root of G over E xu times V prime. Okay? Now what we want to compute is the geodesic curvature here, which is defined to be this. Okay, I'm going to use this board space here, okay? And so you say, okay, geodesic curvature is beta double prime of S. Well, I have a formula for beta double prime of S. It's right there. See? It's not even that complicated. And U cross T, oh, well, that's just right here, right? So I want to take this dot product that. Okay, well, I have a bunch of XUU terms. Oh, XUU. Remember those formulas, 3.4.3 from last time? We had formulas for XU and XV, but also XUU, XUV, XVV. Okay, when we were computing the formula for the Gauss curvature, right? We had these formulas for XUU, XVV, and XUV. And this formula is 3.4.3 in the book, 3.4.3 in the book. And you plug everything in and simplify it. Just it's a bunch of algebra at this point. And when you plug in the formulas for XUU and XUV and so on, and then take the dot product of this with that, because what are you going to have the dot product with? You're going to have an XUU dot product, an XV and so on. Simplify everything. You get this equals that. And it's just algebra from this point on. Yes?
Does the existence of a formula for geodesic curvature that doesn't use the unit normal imply that it's a property that doesn't need it?
Yeah, you put your finger on the key point here, which is like, who cares about the formula? No one cares, okay? We're going to use it to prove something, okay? In a second, called the Gauss-Bonnet formula, right? It's actually pretty important. But the key point is that you can see that what this depends on and what it doesn't depend on. Geodesic curvature, this is all something the ant understands. This is all something the ant understands. The ant understands E, F, and G, and U and V, that's just their latitude and longitude, right? And their coordinates. And so the ant can compute all this stuff. It can compute all this stuff. So it just needs, as long as they know their path and their coordinate chart, and they know the E, F, and G's in their coordinate chart, then they can compute their geodesic curvature. And guess what? Geodesic curvature, in this case, because we see where it comes from, it's just, we understand where it comes from. It's really based on our notion of curvature that we had before. So in fact, it still is just theta prime of S. If you measure theta in radians, and S is unit length, okay? S is arc distance of the curve. Then the rate of change of your angle when you measure in radians is, in fact, what the geodesic curvature is. And it's positive if you're curving to the left, and your normal's out. And it's negative if you're curving to the right. Okay. And that's it. That's what geodesic curvature is. And we can use this formula to prove some cool stuff. You see this messy formula? What does it remind you of? It's a messy formula for Gauss curvature, right? Turns out they're connected. And what we're going to show is that if you have something that's topologically a disk, right? Take a disk here. And it doesn't have to be a flat disk, by the way. So topologically a disk, I mean, we're thinking of it in 3 dimensions, right? And it's, but it's not necessarily flat, right? But think of this as topologically a disk, and you have the boundary of the disk. What we're going to be able to prove is that if you take the double integral over that disk of the Gauss curvature times the area form, remember this is the thing, integrate to get area, just multiply that by the Gauss curvature at every point. That's a 2-dimensional integral, right? And you add to that the integral over the boundary, right? The boundary is a 1-dimensional integral, just around this boundary. Now on that boundary, there's a notion of curvature. How much are you curving to the left as you go walk around the boundary, right? Some places you might even be curving to the right, but not in the picture. And you take the geodesic curvature there, ds. This always equals 2 pi. Right, and that's the Gauss-Bonnet formula. So what you can see is the integral of the Gauss curvature plus the integral of the geodesic curvature on the boundary, it adds up, they kind of cancel, right? And they add to something, it's the same thing every time. And by the way, if you have a flat disk, like an exactly flat disk that's in a plane, right? And it's a disk of radius r, capital R, then the geodesic curvature is just 1 over r, right? And you integrate it over something of area of length 2 pi r, you get 2 pi. So you can, and that's a flat disk with the Gauss curvature 0, so you get 0 plus, that's 2 pi r times 1 over r equals 2 pi, so you can check it in that case. And here's another case you can check it in. Half a sphere. So take a sphere, erase the southern hemisphere. No offense if you're from the southern hemisphere. The equator there is a geodesic. Can we agree that if you're walking on the equator, the ant is walking in a straight line from their perspective the whole time? So the geodesic curvature here, so in the first case, the Gauss curvature is 0. In this example, the geodesic curvature is 0. So this term is 0. But the Gauss curvature, we know, is 1 over r squared, and the surface area is 2 pi r squared, and you get 2 pi again. And so that's the 2 examples you keep in mind to remember what that constant is. And then this is the sort of the first connection we have. So maybe we'll be proving this pretty soon. Maybe not tomorrow. Maybe not on Wednesday, but pretty soon. All right. Good work. See you guys next time.